Bismillahirrahmanirrahim. Assalamu alaikum, dear students. We are now starting the second lecture for the week number 6 for wireless and mobile communication course. If you recall, in our last lecture we started discussion on diffraction and we briefly talked about the Fresnel zone concepts, and we discussed that diffraction generally cause losses, but it is also beneficial in the sense that because of the diffraction the waves they become available in the shadowed region as well, which are not covered from line of sight propagation. So how can we explain the diffraction phenomena? Our common explanation onto this diffraction phenomena is through the Huygens principle. Huygens principle states that all points on a wavefront of a wave, they can be considered as a point sources for producing secondary waves. So if a wave gets diffracted, then the wave fronts which are available in the undifracted path, they also generate new wavelets which are named as secondary wavelets, and those secondary wavelets, they also propagate to the region which is blocked by the line of sight communication, blocked by an obstruction to prevent the line of sight communication. These wavelets, they combine together to produce no new wavelets in the propagation directions. So if you have a wave which is coming from this side here, and this one is got blocked here, so any point here on top or here, they will also generate new wave fronts. So it will generate a wave front like this here. Similarly, this one also create a wave front like this. The third point would create a wave front like this, and so on. So all these points will be creating wave fronts. So eventually they will be having a resultant effect of having a wave in this region as well. So this diffraction phenomena, it causes the propagation of secondary wavelets into the shadowed region, because these secondary wavelets generated from the points, it will have a wave front somewhat like this, which goes in the region which is actually blocked by this obstruction OBS mentioned here. So the question is, how can we calculate the gain or alternatively loss encountered because of this diffraction? So a common model in order to calculate the loss is known as knife edge diffraction model. Typically this path, it can be blocked by any physical object. Maybe if there is a hilly area between transmitter and receiver, of course those hills would block the path, or if there is a large building between transmitter and receiver, they would obstruct the path, or any other physical object can can obstruct the path between transmitter and receiver. But practically it is not possible to model each type of physical environment, because the physical obstruction can be of any shape or any dimensions. So the most common model is known as the knife edge diffraction model, where we model the diffraction by a knife edge, which is illustrated here. So this edge, this is actually a very narrow screen of virtually 0 width, is very small. This width is very small. Actually, the corner, this has an obstruction here, and we are assuming that this screen is actually extending towards infinity in the perpendicular plane. So the plane which is coming inside and outside of this this paper would be carrying an infinite width of this screen. So we assume that this screen of height h, height of this obstruction is h. This particular height of obstruction is blocking the path between transmitter and receiver. This obstruction is placed at a distance d1 from the transmitter and d2 at the receiver. So this line of sight path gets blocked, and the wave goes towards this edge of this screen, and this after diffraction it gets bent and it goes towards the receiver. Although in this figure I have illustrated that the transmitter and receiver, they are at same height, but practically it is not necessary to have transmitter and receiver at the same height. So you would see that the transmitter and receiver would be ideally be at different heights. So the direct line of sight path is this one, but wave propagates through diffraction, so it gets diffracted from this this sharp object and then goes to the receiver. So one thing you should note that there would be a path difference between this direct line of sight path and this diffracted path. You can imagine there is a difference, and we can estimate the how much difference we can have, because it's a regular geometry, you can see, and by using the geometric principle we can calculate the path difference. And in fact, while doing the two-ray refraction model, we tried to calculate a difference as well. So similar procedure can be adopted here to calculate the difference. And if we simplify, we will see that the path difference between these two paths, the direct line of sight path and the diffracted path, would be approximated by this relationship h square by 2 d1 plus d2 upon d1 d2. One thing is that we are taking some assumptions here, although these are assumptions, but they are very practical assumptions, because generally the distance between transmitter and receiver is much larger as compared to the height of the transmitter and height of the receiver. So we are assuming that the height of the transmitter and receiver and height of this obstruction here, they are actually small as compared to these distances d1 and d2. And secondly, this height of obstruction is actually much greater than the wavelength of the wave which is being used for propagation. So this approximation is made on these assumptions, and after that we get this path difference to be equal to this value. Secondly, it is a common practice to simplify this calculation for having this path difference. Actually, if you draw a horizontal line here, you can see that the bottom part of this is actually the same height. This is HR height, HR here, this height is HR. So we are interested in the phenomena which is occurring at this upper side only. The bottom side is actually not related to our calculation. So in most cases we generally simplify this geometry by reducing all the heights which are available here by this HR height, because this HR is the minimum height. So everything goes is shifted downward. You can see that this receiver becomes at the height of 0, and obstruction, it becomes at height of obstruction minus HR, and the receiver side, it becomes at height of ht minus HR, because we have reduced the height of HR from all the possible heights. With this reduction in height, we get a relatively simple geometry here. You can see that it's a relatively simple geometry here, and we can use this geometry to make the necessary calculations. The path difference that we observe is given by this relationship. Actually is 2 pi by lambda, as we have discussed in the case of two-ray ground reflection model as well, 2 pi by, because in 1 lambda propagation the difference is 2 pi, and if you multiply with the path difference you will get the phase difference here. So we are multiplying this path difference by 2 pi by lambda, so to get this phase difference. Secondly, because these angles they are assumed to be small, so if these angles they are small, in that case these tangents they are approximately equal to their angular values. In that case we can approximate this alpha to be equal to sum of this beta and gamma. So you can directly see from this geometry here that this alpha plus beta would be beta plus gamma would be equal to this alpha, and this alpha it can be calculated from this geometry, from this triangular shaped geometry, and if you calculate this thing, so you would see that alpha can be approximated as h d1 plus d2 upon d1 d2. In calculating the loss for the this knife edge diffraction model, there is another parameter which is known as Fresnel-Kirchhoff's diffraction parameter. This is actually a normalized parameter without any dimensions. It's a dimensionless value. So this normalized parameter is used to simplify these results. This Fresnel-Kirchhoff diffraction parameter is represented with this expression. Nu is actually h, which is height of that diffraction, which is illustrated in the previous diagram. Yeah, and under root of 2 d1 plus d2 upon lambda d1 plus d2. This h is actually height of diffraction, which is actually shown here. This is h. So this can be represented in terms of alpha. So this alpha is actually alpha, which we have shown in the previous slide. This h d1 plus d2 upon d1 plus d1 d2. We can represent this nu in terms of alpha by using this relationship, and similarly the phase difference can also be represented in terms of nu, which is phi is equal to pi by 2 nu square. So you can see that this phase difference is dependent on nu, which is actually dependent on the height as well as the distances from transmitter and receiver. So actually all these parameters they determine how much phase difference would be there when we talk in terms of diffraction. These are three different scenarios you can see from the diagram here. First scenario where this obstruction it completely blocks the path between the transmitter and receiver, or in other words height of this obstruction is actually higher than the height of transmitter as well as the receiver. In that case we take h to be positive, and both alpha and nu they are taken as positive values. Another scenario is that when the transmitter, receiver and this obstruction they are actually at the same height, so all of them they are at same height. In that case h, the height of obstruction would become equal to 0, because it's is calculated with reference to this LOS path, which is actually 0, and eventually this alpha and nu would also become 0. The third case is the one where we have obstruction, but still there is a direct line of sight path available between transmitter and receiver. In other words, height of obstruction is smaller, that it does not block the line of sight path, but it does block some of the Fresnel zones. So it will cause some loss, but it still the line of sight path remains available. In that case we take height to be negative, and eventually alpha and nu there will be negative values. How to calculate the loss? Actually, we generally for Fresnel diffraction, we generally work in terms of the diffraction gain, and loss will be negative of that gain. So the diffraction gain is actually defined in terms of this f nu, which is complex Fresnel integral, which is defined here. This complex Fresnel integral is actually ratio of the E field, diffracted field to the E field values, and this f nu, which is the Fresnel integral, is given by this expression. And if we calculate the magnitude of this Fresnel integral and take log and multiply by 20, so we get this gain because of the Fresnel diffraction in decibels. So this diffraction gain is illustrated in the diagram here. The horizontal axis is Fresnel diffraction parameter nu, and the vertical axis is the gain. You can see that the gain gets reduced as we increase the Fresnel diffraction parameter here in this direction. This expression, this graph and calculation of this integral is actually not straightforward. Generally, numerical integration is used to calculate this complex Fresnel integral. However, for the calculation of the loss, we generally refer to some other approximations. So the approximate values of this graph, they are given here. For different values of nu, if nu is smaller than -1, then this gain can be taken as 0. If nu is between -1 and 0, the gain is this value, and so on. So if for different values of nu, we can estimate the gain, which is illustrated here. So using this relationship, we can calculate the gain, or if we take the negative of that, we will calculate the loss as well. So let us take some problems related to this diffraction loss. So we want to calculate the diffraction loss for the three cases shown in the previous figure. We can refer to three cases here. You have these three cases. You can see that in one case the line of sight path is totally blocked, in other case h is 0, and third case h is negative. So we have h to be equal to 25 meter. For B part we have h equal to 0, and for C part we have h equal to minus 25 meters. The wavelength that we are using is actually 1/3 meters. Distances from transmitter and receiver, they are given as 1 kilometer each. So we will compare the result with the actual graph here, which is illustrated here. So you can calculate the gain from the graph as well as these approximate relationships which are shown here. So let us start our calculation for h is equal to 25. We know these given parameters, and if we substitute these values, we can calculate the value for the Fresnel diffraction parameter nu. You can directly substitute all the values, and you would see that this nu comes out to be 2.74. And if you calculate 2.74 is somewhat here, and from here you can see if you draw a vertical line from here and here, you would be able to estimate the gain from the diffraction from this graph. If we estimate this gain from the graph, it comes out to be 22 dB. But if we use this relationship, because we are having value of nu which is 2.74, and nu greater than 2.4 means we have to use this relationship, GD equals to 20 log of 0.225 upon nu. So if you use this relationship, you would see that this loss comes out to be 21.7 dBs. Secondly, if we like, we can also calculate the path difference, although it's not asked in the question, but as we have derived the relationship, we can directly use them to calculate the path difference as well as the phase difference between them. We can see that the path difference here is delta is equal to h square upon 2 d1 plus d2 upon d1 d2, you can simplify it to find the path difference, which comes out to be 0.625. This path difference is actually important in calculating how much difference, how much Fresnel zone is obstructed by the obstruction. We have we know that this delta is actually n lambda by 2 for Fresnel zones. We can calculate this n here. You can see that n would be 2 delta upon lambda, because we know the path difference here, so we can calculate n, which is 3.75. so actually this obstruction which is represented here is obstructing 3.75 of the Fresnel zone, or in other words, it's completely blocked the first 3 Fresnel zones by this obstruction. Okay, now we move on to the second part, where we have the height to be equal to 0. If we have height equal to 0, in that case the diffraction parameter nu would be equal to 0, and nu equal to 0 from graph, from this relationship, you can see that if you have nu equal to 0, you can substitute in this expression to calculate the gain, and you would see that this diffraction loss comes out to be 6 dB, and the same comes from the graph as well. So there is a 6 dB loss when the height of the obstruction is 0. In other words, when the obstruction is at the same height as for the line of sight between transmitter and receiver. So we have only 6 dB of loss. How much diffraction zones would be obstructed? You can see that it's actually, because they are at the same height, so only part of the first Fresnel zone would be obstructed, because the half of the Fresnel zone, which is the lower side of the diffraction, comes here. So it's only obstructing the first Fresnel zone, which is here. It's the upper part of the first Fresnel zone is free, so it's only obstructing the lower part of the Fresnel zone. So the obstruction is in the middle of the first Fresnel zone. Let's move on to the third part, which is h is equal to minus 25 meter. In that case, the Fresnel diffraction parameter is calculated to be minus 2.74, and if it's minus 2.74, you can see that this diffraction loss from the diagram, it's shown here, somewhere here. Okay, 2.74 would be somewhat here. There will be some loss here. You can see this loss comes out to be 1 dB only from the graph, but numerical approximation, this one, because nu less than minus 1 corresponds to the loss equal to 0, so this nu minus 1 would give a 0 dB loss. And if you calculate the height, how much Fresnel zones would be obstructed, so it's actually the first 3, as the positive height h, the same value, it was obstructing the first 3 Fresnel zones. The negative value of the same would be actually obstructing only the lower part of the higher order Fresnel zone, like 4th or 5th and 6th Fresnel zones. So because most of the Fresnel zones, they are free, so you would see that there is no significant loss, and practically you can take that loss equal to 0 dB. So for negative value of h, we do not encounter any amount of loss here for this particular case. So let us move on to another problem. So we have another scenario which is illustrated in the diagram here. So we have a receiver which is at 25 meters height. We have a transmitter which is at 50 meters height, So HT is 50 meters and HR is 25 meters. The knife edge, which is illustrated here, is actually 100 meters. So it's actually obstructing the path between transmitter and receiver. So this line of sight path is obstructed by this knife edge. The distances here from the transmitter, this distance is 10 kilometers, whereas from the receiver the distance is only 2 kilometers. If we are assuming that the operating frequency is 900 megahertz, in that case we can calculate the wavelength, which is calculated by dividing the speed of light by the frequency of operation. So if you divide 3 into 10 to the power 8 by 900 into 10 to the power 6, so you would end up with the wavelength of 1/3 meters. Okay, so this is the geometry that we need to work on. So first thing what we want to calculate is how much loss would be there if we have this sort of knife edge blockage between the LOS path between transmitter and receiver. Secondly, we want to have know the height of the obstacle, and that means we want to have height h which corresponds to the loss of 6 dB. Recall that in the previous example we did this calculation as well. If we have height to be equal to 0, in that case we have a loss of 6 dB. So 6 dB loss corresponds to the case where the height of obstruction is 0. In other words, the height of obstruction is actually from the same height between so it's actually same as the height of the LOS path between transmitter and receiver. So let us start our calculation. As I said, one of the simple scenarios to make this calculation is to reduce the height, because this receiver has a minimum height. So if we reduce each height by this 25 meters here, so all the heights would be reduced by 25 meters. So you can see that this receiver height would go to 0. This obstruction height, because initially it was 100 meters, but now it would become 75 meters, and transmitter height, which was initially 50 meters, that will come out to be 25 meters. So this is the very common assumption to calculate the heights here. Second thing related to this knife edge diffraction is the calculation of knife edge diffraction parameter. If you go back directly, you can see that the knife edge diffraction parameter is actually this nu is dependent on this alpha, and if we can calculate the alpha, we can also calculate nu, and alpha is actually related to the angles in the geometry, this beta angle and gamma angle here. So let us go back here. So this is our problem. This gamma angle is illustrated here. You can see that this part of the geometry, this one is a triangular geometry, and you can use simple triangular trigonometric relationship on this triangle to calculate this gamma. And you can see that this gamma is actually tangent inverse of this perpendicular, which is 75 meters, divided by base, which is 2 kilometers or 2000 meters. So if you simplify this thing, you would see that this gamma is 2.15 degrees. Secondly, beta is also corresponding to another triangle. If you look at this triangle, if I draw a horizontal line here, you would see that we will have a right triangle here. But for this right triangle, because this height is 25 meters, you can see that, so this perpendicular would be 50 meters only, which is actually difference of this 75 meter and this 25 meter. But the base is 10 kilometers, so this beta is tangent inverse of perpendicular upon base, which is 75 minus 25 upon 10 kilometers, which means 10,000 meters. So if you simplify this thing, you would see that the beta comes out to be 0.2865. and from this values of beta and gamma, we can estimate the value of alpha, which is given as sum of this beta plus beta and gamma. So if we add these two, you would see that it's approximately 2.4, which comes out to be 0.042 radians. So alpha is 0.042 radians, and if we substitute the value of alpha in the relationship for nu, the diffraction parameter, which is shown here, so nu is actually defined by this alpha relationship, alpha into under root of 2d1 d2 upon lambda upon d1 plus d2. So if we substitute in that relationship, you can see that this is alpha, and this entire is actually these are distances, and this is wavelength. If you simplify this thing, you would see that this comes out to be 4.24. So the diffraction parameter comes out to be 4.24. We can calculate the loss from this diffraction parameter by referring to the graph which is shown previously, this graph, or we can use the approximate relationship which are illustrated here. Since our parameter is greater than 2.4, so we would be focusing on this relationship which is shown here. So if we use those relationship, you would see that the loss, diffraction loss, comes out to be 25.5 dB. For the scenario given in this problem, we would expect a diffraction loss of 25.5 dB. Now let us move on to the second part of the problem. The second part of the problem is actually requires the reverse calculation related to what we have done so far. In this case, we know that how much loss is there is 6. We are interested in having 6 dB loss. So how much height is required for the diffraction area? So if you look at this figure here, this is the line of sight path between transmitter and receiver. If I ask you to have 6 dB loss, as we have discussed previously, that 6 dB loss is corresponding to the parameter where nu has a value of 0. Having nu equal to 0 value would illustrate that that this knife edge have the enough length which is equal to this this LOS path. So actually we are interested in calculating this length, which I have indicated in red here. So we are interested in having this length. So let me try to make a geometry which represents this scenario. So we have a transmitter here which is 25 meters, because we are working on the reduced geometry, and secondly the receiver antenna is at the height of 0. This obstruction is represented here, H is represented here. So you can you would be having a geometry which is somewhat like this. Okay, now if you focus on this geometry, actually you can see that there are two different triangles in this geometry. First triangle is this one, which is illustrated here, and if I ask you to calculate tangent of gamma here, you would see that this tangent of gamma is actually perpendicular upon base, which is h upon 2 kilometers, which is 2000 meters. So this tangent gamma can be calculated from this geometry, and this comes out to be h upon 2000, so which is shown here. Okay, There is another geometry here. You can see that if you take the geometry from the transmitter end, we have a right triangle which is coming from the transmitter. For this particular case, the base is 10 kilometer plus 2 kilometer and the perpendicular is actually 25 meters. In that case, we can again calculate tangent gamma because the gamma angle is same for both the geometries. So in that case, tangent gamma would be equal to 25, which is perpendicular, divided by this entire base length, which is 12 kilometers or 12,000 meters. So you can see that by comparing these two geometries, and because both the geometries they are focusing on the same gamma, we can relate this height, this ratio of first triangle to the ratio to the second triangle. So we have this fraction which is represented here. So h upon 2000 is equal to 25 upon 12,000, and by simply simplifying this relationship, you would see that the h comes out to be 4.16 meters from this geometry. So if we have obstruction height which is equal to 4.16 meters, in that case you would be having a loss of 0 dB. But you at this point I want to clarify that this h of 4.16 meters is actually with reference to height of the receiver, because we are working on the reduced height. The original geometry is like this. The original geometry, the receiver antenna was at the height of 25 meters, and for simplification we reduce the height, each height by 25 meters. So we take the receiver antenna height to be 0 meters. So this height h 4.16 meters, it's actually representing the height which is above the height of receiver. So if I refer to this geometry again, and I want to ask you what will be the total height of this knife edge diffraction to have a 6 dB diffraction loss, in that case you would be required to add this 25 meter as well. So this will be 4.16 meter plus 25 meter or 29.16 meters height. So this was the problem related to calculation of the diffraction, knife edge diffraction parameter. So with this I would conclude our topic here, and let me quickly summarize important points related to our discussion in this knife edge diffraction. So the important thing that we need to know that is having clear line of sight is not enough in order to have lossless propagation. Even if a part of the first Fresnel zone is obstructed, there is a loss which is encountered during propagation. So in order to have minimum amount of loss, we need to have at least 55% of the first Fresnel zone clear from any obstruction. Secondly, as the obstruction height increases, the loss also gets increased, which is generally represented in terms of this Fresnel diffraction parameter nu. So we have Fresnel diffraction parameter. If we have Fresnel diffraction parameter which is positive, that corresponds to high loss. That means if diffraction is obstructing significant amount of the Fresnel zones. If the Fresnel diffraction parameter is equal to 0, or the height of obstruction is same as the line of sight path, in that case we still have loss which is equal to 6 dB. If the obstructions is lower than the LOS path, even in that case there is a small amount of power. Like in one of the problems we had the loss of 1 dB, but that loss is practically not significant. So if the height of diffraction this obstruction is smaller than the LOS path, in that case we can ignore this diffraction loss. and we can calculate this diffraction loss from this curve as well as from these approximate relationships. So this concludes our discussion on the diffraction loss and the Fresnel diffraction, and we use the knife edge diffraction parameter in order to have in order to practically calculate numerically calculate the diffraction loss. So we stop our discussion here. Inshallah, we'll start a new topic in our next lecture. So thank you all.